and we are going to solve the potential. So first we have to know about the Dirac delta function. So the Dirac delta function is denoted by del x, and it has the property 0 at x not equal to 0 and infinity at x equal to 0, and the some other properties are integration minus infinity to plus infinity f of x, any function of x, del x dx is equal to f of 0. So now we are going to solve the Dirac delta function potential. So let's take a potential v equal to minus alpha del x, where alpha is a constant. Now to solve this, first we have to write the Schrodinger equation. Schrodinger equation minus h cut square over twice m d2 psi dx square plus v function of all x psi x e psi x. Now by putting the potential minus alpha del x psi x e psi x, now we have to solve this equation. Okay, so first the Dirac delta function looks like, if we're plotting a graph like this at x equal to 0, and this is going to infinity, has an area 1. So to solve this equation, first we have to solve it for two different cases. First case, for the bound state where is lesser than 0, and second case for the scattering state where E is greater than 0. Now in this video I am only going to talking about the bound state. So for the bound state, so now as you can see, this bump, delta function bump, is only at x equal to 0. So there are two different regions for x is lesser than 0 and for x is greater than 0. So first for the bound state I am going to solve it for x is lesser than 0, and then for x is greater than 0. So first write this Schrodinger equation plus 0, as the potential is 0 elsewhere, and at 0 x equal to 0 the potential is infinity. So I'm putting 0 here. For x is lesser than 0 is equal to E psi, which is our energy. Now d2 psi dx square is equal to minus twice me over h cut square psi. Now as E is lesser than 0, so the total quantity minus twice me over h cut square is positive. So I am going to choose a constant k which is equal to minus twice me over h cut square and its root. So now this quantity k is a real positive number. If I choose only twice me and I omit the minus sign, so it becomes complex quantity and it's getting tough to handle this kind of equation. So now the equation becomes k square psi. Okay, so d2 psi dx square minus k square psi is equal to 0. Now we have to solve this ordinary differential equation. To solve this kind of ordinary differential equation, I have choose psi equal to e to the power mx, where m is any kind of constant, and then double differentiate it with respect to x, it gives m square e to the power mx. Now putting this value on the equation, differential equation, I get m square e to the power mx minus k square e to the power mx is equal to 0, and from that I can easily get m square equal to k square and m equal to plus minus k. So my solution, what I am choosing was e to the power mx. Now putting the value of m with some constant, it's like this, where a and b are constant which we have to find. Okay, so now here in first case where x is lesser than 0, for this region this part is blows up. Why? Because at x is tends to minus infinity, this term blows up. I can easily show that the curve e to the power minus kx is like this. So for minus infinity, you can easily see that this becomes 0. So at x equal to 0, it is 0. Putting x equal to 0, it is 0, and at x tends to minus infinity is 0. There is nothing. So the solution will be only b e to the power kx. Okay, and now we have to solve it for x is greater than 0. So it's like the same. We will again have the same solutions. Now I am right with different constants. Okay, like this. Now this time this term will blows up, and I can easily show that the curve of e to the power kx is like this. So at x tends to infinity, the psi has to be finite. So this term has to blows up. Here also the same case, at x tends to minus infinity, the psi has to be finite. So that's why this is also blows up. So you can see that here is nothing present here. So that's why this is 0, and now I get these two solutions. So now my solutions are psi equal to b to the power kx for x is lesser than 0 and c to the power minus kx for x is greater than 0. Now we have to find the value k, constants k, c and b. So for this I am going to use two properties of the wave function, and the first one is psi is continuous everywhere. Okay, and the second one is d psi dx is continuous except at the points where the potential is infinite. So from the first condition we can easily get this equation: psi at x equal to 0 is b e to the power 0 for x is lesser than 0. So we get b, and psi at x equal to 0 for c e to the power 0, x is greater than 0, we getting c. So now psi has to be continuous, so that's why psi plus, I'm denoting plus for x is greater than 0 region, is equal to psi minus. So from this b equal to c. Okay, so from this, as c is equal to b, we get this. And now we are going to use the second property, which tells us that d psi dx is continuous except that point where the potential is infinite. So to use this particular theorem, let's do something else. So now I am writing the Schrodinger equation, which is like this. Now what I am going to do is to integrate this equation from minus epsilon to plus epsilon, where epsilon is a positive quantity, and then I'm going to use limit epsilon tends to 0. So that really not changing the real definition of this equation. So what I'm going to use is integrate it over minus epsilon to plus epsilon like this. Psi x dx. Okay, so and now I am going to use the limit epsilon tends to 0. So epsilon tends to 0 minus epsilon to plus epsilon alpha del x psi x dx equal to limit epsilon tends to 0 minus epsilon to plus epsilon e psi x dx. Now this quantity is 0. As you can see, it is easy to show that limit epsilon tends to 0 is a constant, so I can write it here, and yes, you can easily see that this quantity is 0. Now I have to calculate for these two. Now for this one, limit epsilon tends to 0 alpha, which is a constant, so I can write it here. So minus epsilon to plus epsilon del x psi x dx. As I can show you earlier, for any delta function integration like this, it gives us psi 0. right, as to plus infinity f of x del x dx is equal to f0, like this. So now this becomes alpha psi 0. Okay, and now I have to solve it for this particular one. Okay, so write it properly. This is a constant term, so I can write it here. To solve this, I can easily write d2 psi dx square as d dx of d psi dx dx. So this gives us tends to 0 d psi dx, right? As it's cancel out, and you know that by integrating a particular function's derivative, it gives that function. So I am going to write this term as del d psi dx. So I get that square twice m del d psi dx. So now rewrite this equation. I get minus h cut square over twice m del d psi dx is equal to alpha psi 0. Okay, so now del d psi dx gives us twice m over h cut square. There is a minus psi 0. So now we have to solve this. Okay, the wave function was like this, and now we are going to put the value in this particular equation. Okay, so for psi x b to the power kx for x is lesser than 0, so d psi dx k p e to the power kx, and d psi dx at x equal to 0 is kb. I'm going to write this d psi dx minus because the region is x is lesser than 0, so I'm writing it minus to denote this. Okay, and the next part, psi x is b e to the power minus kx for x is greater than 0. Differentiating it with respect to x, I get minus kb to the power minus kx. Same, putting at x equal to 0, we get minus kb, and then I'm writing it as plus, as this is the x is greater than 0 region, minus kb. So del d psi dx, which means d psi dx plus minus d psi dx minus is equal to minus twice m alpha over h cut square. Now psi 0. Now what is psi 0? So the wave function at x equal to 0. For the both case, if I put x equal to 0, we get only b. So psi at x equal to 0 is b. So minus kb is equal to minus twice m alpha over h cut square b. So minus twice kb, the minus twice m alpha over h cut square b. So what do we get? Okay, so k equal to m alpha over h cut square. So as we denote k as root over of minus twice me over h cut square, putting this value m alpha over h cut square is equal to root over of minus twice me over h cut square, squaring both sides, we get this. Okay, it's cancel out. Let's cancel out this, and we easily get m alpha square by twice h cut square followed by a minus. So this is the energy eigenvalue. Now we know the k is equal to m alpha over h cut square. So we have to find the constant p. So you can easily do that by using the normalizing condition, which says that minus infinity to plus infinity psi star psi dx is always 1. So that means the probability of getting the particle from minus infinity to plus infinity is always 1. So minus infinity to plus infinity psi star. Now psi star means the complex conjugate of the wave function psi. Now, so our wave function was psi b e to the power kx for x is lesser than 0 and b e to the power minus kx for x is greater than 0. So to use this, we have to break the limit from minus infinity to 0, for which this will be the desired wave function, and then from 0 to infinity we will use this. So now as you can see, there is no I dependent term. I means the complex root over minus 1. So the complex conjugate of b e to the power kx is also b e to the power kx. So we get equal to 1. So mod of p square. So I'm just using the divide the integration in two parts, and okay, so there is a mistake, sorry. For another part, 0 to infinity, we have to use this. So we get mod of b square to the power minus twice kx dx is equal to 1. Now it's correct. So minus infinity to 0 e to the power twice kx dx plus 0 to infinity e to the power minus twice kx dx is equal to 1. So mod of p square, it gives e to the power twice kx over twice k minus infinity to 0 plus e to the power minus twice kx over minus twice k 0 to infinity. So what do we get? 1 by twice k, this gives 1, this gives 0, minus 1 by twice k, this gives 0, this gives 1. So okay, so we get p square over k is equal to 1. So p is equal to root over of k. So now our wave function is psi is equal to root k e to the power kx for x is lesser than 0 and root k e to the power minus kx for x is greater than 0. Now we can write this wave function like using k is equal to m alpha over h cut square. So this gives root over of m alpha over h cat square e to the power minus m alpha over h cat square mod of x. Okay, so if x is negative, so this becomes positive, we get this wave function. If x is positive, this becomes negative, so we get this wave function, and our solution is psi, the wave function, is equal to this, and the energy is minus m alpha square over twice h cat square. Thank you.